Alright, so for this video, we're going to be talking about where your muscles get energy from. And, it isn't, sometimes it's going to be the places where you think that they're getting it from, but some of them are probably going to be a little bit new. But hopefully by the end of this, you might understand a little bit more about, what energy drinks are trying to do and why they're probably not doing it right. Alright, so when you exercise, you get tired. This is not going to be a surprise to anyone out there. But why you get tired and when you get tired is actually kind of interesting. Your muscles use a lot of energy. Like when you're using them, right? Like, if you're just sitting around, you can use your muscles all you want. But when you are like actually exercising, running or something like that, your muscles are burning energy to move much faster than they can make that energy. Especially right at first. When you first start to run, your heart isn't pumping yet, your sympathetic nervous system hasn't kicked in, you're not getting enough oxygen to your muscles. So they are at that point making energy way slower than they are using it. But your strongest muscles, your fastest muscles, can actually use energy far, far faster than you can get oxygen to them to make energy through the normal way. So that's part of why you get tired. It's only part. So here we have a little guy, and he is sprinting. All right? He's sprinting for like maybe 2 minutes. All right, which is about as far as you can sprint. You cannot sprint for more than a couple of minutes. You just can't. No one can. Maybe like the world's best sprinter could sprint for like 3 or 4 minutes, but there's just a limit to how much energy your muscles can store. So when you first start running, your muscles are making ATP through the normal way, using oxygen. Now you suddenly start using a lot of energy, and you aren't delivering a lot of oxygen to your muscles yet because your heart hasn't started pounding. Fortunately, your muscles have a way of storing oxygen. They basically got a little savings account full of oxygen that they can use. They'll use that oxygen up pretty fast, but they've got that little bit there. Then you have your ATP reserves, and you will burn through your ATP reserves very, very fast. But your muscles have a special reserve where they can actually they can squeeze their ATP to get some extra energy out of them. And that'll get you to like maybe 40 seconds. At that point, you're looking at fermentation, because you don't need oxygen for fermentation. Oxidative metabolism is slow. You can only do it as fast as you can get oxygen there. And even if you had a bunch of oxygen there, it's just not the fastest way to make energy in the world. Glycolysis is really, really quick. So you can burn through your sugar. You're only getting 2 ATP per sugar that you're making with lactic acid fermentation, but at least you're getting something. And you can do that for a little while. And then once you burn through all your sugar, you've released all your glycogen, you burn through all your ATP, you don't have any oxygen coming yet. At this point, your heart better be thumping, because now all of the ATP that you're going to be making with oxygen. And so that's when you'll start to slow down. You can't sprint past that point. And you'll still keep running, but different muscles are engaged. All right, so we're going to separate energy in your muscles into three categories. The first is immediate energy. This is the energy that you get for like 6 seconds of intense activity. Maximum output for that first 6 seconds. You got basically three sources of energy. First, you have the ATP that's already in the cell. You'll burn through that in about a second. Second, myoglobin. So, myoglobin, as you might guess from the name, myo means muscle. Globin sounds kind of like hemoglobin. You think, what's hemoglobin? Well, hemoglobin is the protein in blood, in red blood cells, that transports oxygen. Myoglobin is a very similar protein. It holds oxygen, it binds oxygen. But instead of moving around your body, myoglobin is found in your muscles. So when you're at rest and you're not, exercising or something like that, when your blood goes by your muscle cells say, hey, I don't need that oxygen right now, but I might later. So I'm going to steal some of that oxygen, stick it on my myoglobin so that I got a bank account full of oxygen that I can use should I need to run away from a bear. Y'all have seen myoglobin before, though you probably don't know it. Like if you take a look at steak, like you buy a steak from the store, right? And you take it out of the package, and there's this like pinkish liquid that's usually around the bottom of the steak. And a lot of people think it's blood. Some people think it's like dye that they put in there. It's neither. It's actually myoglobin. Hemoglobin is sort of a dark crimson red. Myoglobin is sort of a pale pink. And like basically what steak is it's cut muscle. So you cut the muscle and myoglobin leaks out. And that's what is that pink liquid down there. That's myoglobin. And that myoglobin, it holds onto the oxygen, but now bear comes crashing through your wall, you got to run away, right? You burned up your ATP in the first second, and your blood is not pumping yet because, like, it actually takes a couple of seconds for your adrenaline system to kick on. But you're still gonna have to run away. Or let's say you just need to jump really high. Okay? So like you're just gonna bend down and jump. Your muscles, they're not gonna need that energy for very long. But they're gonna need that energy right now to do that jump. They're gonna need a lot of it. You're gonna be using myoglobin to replenish your ATP. And it's very efficient at it while it lasts. Second thing you're going to do is what's called the phosphagen system. Now, the phosphagen system has two parts to it. There's what's called myokinase and creatine kinase. Both of these do the same thing. They both replenish ATP. I'm going to do creatine kinase first. So when you take ATP, let's put that here. Remember that's adenosine triphosphate, so we're going to have 3 P's. Well, that's ATP, right? And you use it. Then you make ADP, so 2 phosphates, and you've lost a phosphate. Well, what the creatine kinase does, a kinase, by the way, anytime you see kinase is an enzyme that moves a phosphate. It's an enzyme that transfers a phosphate. And in this case, what it's going to do is it's going to take creatine, which I'm going to call C, with a phosphate. And this creatine phosphate bond is actually a really high energy bond. It's even more high energy than ATP is. So what you can actually do is this creatine phosphate, your muscles are full of it. It's just chock full of this stuff. And you can transfer the phosphate from creatine phosphate to remake ATP, and then you're just left with the creatine. So your muscles spend energy when you're not running away from a bear to charge this creatine phosphate. It takes more energy to charge a creatine phosphate than you get out of it. So it's not efficient to use, but it's fast. It doesn't require oxygen. And your muscles can be full of a lot more creatine phosphate than they can ATP. Having the right balance of ATP in your cells is like really important. If you have too much of it, it can actually be a bad thing. But creatine phosphate is a much less delicate system. So you can have a whole bunch of this creatine phosphate around. The other thing that you can do, let me just go in here and scrub this away. And this is myokinase. So you've had two ATP, and let's say you use them both. So now you've got two ADPs. And you think, well, ADP, it's not useful. We've already used the phosphate from it. But it's still got this phosphate-phosphate bond, and that's actually a highly energetic bond. There's pretty much as much energy in this ADP bond as there was in the ATP bond. But all of your enzymes are set up to use ATP. But there's still some energy in there. And so what you do is you just transfer this up to here. And what you make is a TP and AMP. Now, this adenosine phosphate bond, that's not as energetic. So you can't really use the adenosine phosphate to get another phosphate to make another ATP. But what this does is it basically increases the amount of ATP that you have by 50%. All right? So you've used two ATP, you can get one of them back. Buy two, get one free. That's basically what this is. I'm going to put this after here. Buy two, get one free. Now these two systems, or all of these, like the myoglobin making more ATP, the ATP that you got in the cell, the fact that every 2 ATP you use, you can get an extra ATP free, and all the creatine kinase that you've got just sitting around inside of this cell, that'll keep you going for about 6 seconds of full-on sprinting. And you better hope that bear isn't chasing after you, because once you get to the end of that 6 seconds, those sources of energy are gone. Fortunately, that's not the end. All right, so that was immediate energy. Now we go to short-term energy. Your muscles have glycogen granules in them. So if you remember glycogen, you have your glucose, and it is in these branched polymers. And it's important that they're branched because you can only get glucose off from the ends. So if they weren't branched, you could only get one glucose off at a time. But since they are branched, they got lots and lots of ends, and you can cut off a lot of glucose at once. Right? So you have these granules of glycogen in and around your muscle fibers, skeletal muscle fibers. They also have them around cardiac muscle as well. We'll get to that later on. So you can start taking the glucose off of your glycogen, and then you can do lactic acid fermentation, glycolysis. And just to remind you guys from the metabolism lecture, what we're going to do is we're going to lysis our glycolysis. That means we're going to cut it in half into two half glucoses called pyruvate. And then we're going to make 2 ATP and 2 NADH. Now, under normal circumstances, this NADH would be really, really useful. We'd send it to the mitochondria. We would do electron transport chain with it. We'd make a ton of ATP. It's a useful thing to have. But our heart hasn't revved up yet. We've been sprinting for 6 seconds. Look behind us, bear's still there. We got to keep running. Heart's not delivering oxygen fast enough to the rest of the body yet. It's still lagging behind. Your brain hasn't even noticed. Like, your brain is still going, oh, what, bear? And you're already out the door. Otherwise, you've been eaten. So, you got to do something to get rid of this NADH. You need to get rid of it, but you can't use oxygen to do that, which is what you would normally do because that gives you lots of energy. So, you got to take the electrons on the NADH, recombine them with the pyruvates, and you'll actually make two lactic acids, and that regenerates your NAD plus, so it can go back to being used over here to make more NADH and allow lactic acid to fermentation to go forward again and again and again. You still keep these 2 ATP. So you made 2 ATP. And remember, buy 2, get 1 free. So you can get technically 3 ATP out of that in theory. And you've got a fair amount of glycogen in your cells, and this is really quick. It's not quite as quick as the immediate energy, but 6 seconds is plenty of time for you to cut apart that glycogen and start this process. So you've got, on average, enough glycogen that you can continue your sprinting for about 30 to 40 more seconds. Obviously, this depends on how in shape you are. But you can keep running away from that bear for about 30 to 40 more seconds and hope it gives up. And it give up by that. Because after that 40-second mark, you're out of glycogen, you're out of creatine phosphate, you've used up all your ATP, your hemoglobin's down, or myoglobin's down. Now you can only use energy as fast as you can make it aerobically. Hopefully by this point, your heart has revved up and is starting to thud oxygen through your body. Adrenaline is coursing through you. It's caused your blood vessels going to your muscles to dilate. So there's a ton of blood going in there, and your heart is going dump, 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 pumping lots of blood, and your bronchioles and your lungs have expanded out so you can take in more air, get more oxygen into your blood. there's still a limit to how fast you can deliver oxygen. Even once your cardiovascular system is totally revved up, your body can only use oxygen, so it can only send oxygen so quickly. And it's actually slower than your fastest muscles, your strongest muscles, can use it. So that's why you cannot sprint a mile. After about 40 seconds, you're going to be slowing down. Your muscles are going to slow down to the speed that you can deliver oxygen to them. Hopefully you've been doing your cardio. Cardio is going to increase your heart health and, increase your ability to deliver that oxygen so that you can run faster, but you're never going to be able to sprint for, minutes upon minutes upon minutes. So hopefully that bear hasn't been doing cardio and at this point is giving up. And you, of course, have been doing cardio, rule 1. And so now you can still use that oxygen to make ATP and continue running away. Not quite as fast as you can sprint, but fast enough. And you can keep doing that for a long time, right? For as long as you have sugar in your blood. Well, not just sugar. You can do this for about 30 minutes, and for 30 minutes-ish, your energy usage is coming from both glucose and fatty acids, about a 50-50 mix. Beyond that 30 minutes, by the way, this glucose is coming mostly from your liver, which stores a lot of glycogen. It's got about 30 minutes of good activities worth of glucose. After that 30 minutes, your liver's starting to run out of glucose. It can still make some more because all that lactic acid that you made, it actually gets shipped to the liver, where the liver builds it back into glucose and then releases it back into the blood. But still, you've got a limited amount of glucose in your body unless you just carb load it or something like that. So after about 30 minutes, your glucose levels drop and your main source of energy becomes fatty acids. This is why, by the way, they say it takes about 30 minutes of aerobic exercise before you start burning fat. That's not exactly true, right? You do burn fat during those first 30 minutes. But the amount of fat that you burns doubles after about 30 minutes. So if you can do 40 or 45 minutes of cardio, you're going to be burning a lot more fat from yourself. They as they say, you will have switched to a fat-burning metabolism. That's what they mean. Now, as this happens, your muscles are going to get tired. If you are doing high-intensity exercise, you're sprinting away from that bear, you have certain sources of fatigue. First off, your muscles are contracting a lot. And they have a lot of action potentials going on constantly. They're constantly being hit with action potentials. What that means is that basically there's not enough time in between every action potential for it to really reset. We say it resets in between each action potential, but the truth is that it takes more time to really reset than you're giving it. So over time, you're causing so many action potentials that potassium, which is normally supposed to be found inside the cell, begins to accumulate outside the cell and in the T-tubules. And you're not spending enough time to get that potassium back into the cell before the next time an action potential hits. And the more potassium that builds up outside the cell, it reduces the excitability. It makes it harder for the next action potential to actually propagate. and eventually can actually just stop the action potentials from happening. Second, you've got ADP building up as you use your energy. Like ADP is now there. And all of the stuff that's going on inside of the cell is based off of equilibrium, which if you don't remember about, you might want to go back and check that lecture. But basically what that means is that like the myosin can bind to ATP. It can also bind to ADP. It has to be able to bind to both of them because it binds to both of them at different points in its cycle. If you've got like 10 times as much ADP as you do ATP because you burnt a lot of your energy, then that means when it goes to grab something, it might grab an ADP instead. And that's going to slow it down. It's going to have to grab that, check it out, let it go, then reach up and grab something else. It's probably still going to be an ADP. So that just slows down the ability of ATP to get into your myosin. That means it's not going to be turning as often. If it's not turning as often, that means it's not pulling as hard. That means you get tired. It's also thought, and this is something that a lot of people used to believe, and some still do, and I would almost kind of put myself in that camp. So there's some idea that that you're making lactic acid, right, through lactic acid fermentation, and that's causing a drop in the pH. So your muscle pH is dropping. It's acidic. Well, acid burns, right? That muscle burn that you feel, they say feel the burn, is in part pain due to the accumulation of acid. And as far as we can tell, the lactic acid does not accumulate in the muscle cell. But that doesn't mean that the acid doesn't necessarily accumulate, because remember that the hydrogen is falling off the lactic acid. If you get rid of the lactate, the lactic part, you might still leave the acid behind. So that one's kind of up in the air as how important it is in the case of fatigue. There's some evidence on both sides, but lactic acid may play a role in muscle fatigue. In terms of low intensity, long duration exercise, like cardio, you're not running your little heart out, you're just taking a good jog, doing some elliptical, or even a power walk. So what's causing fatigue there? Your cells aren't running out of oxygen because it's a low enough intensity exercise so you can get oxygen to them. Well, your cells have run out of glycogen. Your muscle cells have run out of glycogen. After 30 minutes, your liver starts to run out of glycogen, and glucose levels decline. Your brain can sense glucose levels in the blood because actually it only eats glucose. Your brain can't use non-glucose energy sources very well. So it's going to start to panic when it senses glucose levels dropping, and that produces a sense of fatigue. Second, you've been sweating. That means you've been losing a lot of sodium. That means you might be becoming hyponatremic, especially if you've been improperly hydrating, by which I mean hydrating too much, but not with the right stuff. You've been losing a lot of sodium, you've been putting water back in your body, you haven't been putting sodium back in your body, and you haven't been putting enough glucose back in your body to absorb that sodium, so you're diluting what little salt you still have. That reduces the conductivity of your muscles and nerves, making it harder to excite them. You have to put a larger signal down there to get a action potential, and that causes your brain to go, whoa, hold on here, we're getting tired. You also have, all of this basically results in what's called central fatigue, which means that your brain, your central nervous system, is receiving these signals and is interpreting them to mean it is tired. And the brain cells that are responsible for things like moving your arms, moving your legs, keeping you motivated, those cells start to shut down. They become inhibited, at least, and also partially by the release of ammonia from protein metabolism, as your cells are burning protein. Some people have more of a what's called psychological will. Some people have more willpower than others. It's unknown exactly how this is involved, but when they say push through the pain, push through the barrier, stuff like that, it is to a certain extent true. Your brain tells you that you are tired before your body is actually in danger. And it makes sense that it would do that. Your brain's whole purpose is to not let your body get into danger. But, people can push beyond those limits if they're trained to, if they have enough willpower. You can push beyond them, you can run harder, you can train harder, you can run faster. I'm not saying it's safe to do so on a regular basis, but your body has more capacity than your brain is usually willing to exploit. I should also point out that things like adrenaline and panic response shut off those sections of the brain. So when you are actually in a panic because a bear is really chasing after you, or a serial killer just came into your room with a hockey mask and a chainsaw, that amount of adrenaline shuts down those psychological limiting factors, and your brain suddenly becomes quite willing to do damage to your body in order to get you to run away. This is the sort of phenomena where you get 110-pound mothers, lifting and flipping vans to get their kid out from underneath it. And you think, my God, who could do that? Arnold Schwarzenegger couldn't do that. Muscle builders couldn't do that. And here's this little old lady or flipping this van to get her kid out from under it. Adrenaline can tell you to push past those barriers really, really effectively. But it does so at the sacrifice of those limits are there for a reason. That reason is to stop you from doing damage to your body. And, while, they'll flip that man and they'll save their kid, they've often torn their muscles up and done serious damage to themselves doing it. Another factor that plays into endurance is what's called maximum oxygen uptake, or VO2 max. The V stands for velocity in this case. This is basically your ability to deliver oxygen to your muscles. The faster you can deliver oxygen to your muscles in an aerobic situation, the harder you can work those muscles without tiring out. This is a major determinant for your ability to maintain high-intensity exercise for more than a few minutes. There's a lot of things that go into it. Body size is important. It usually peaks around age 20, so age is an important factor. It's usually greater in males than females. Males usually have a greater lung capacity and more responsive airways and slightly larger hearts, even proportionate to body size. Training is one of the most important aspects. It can be twice as much in an endurance athlete as it is in somebody who's untrained. And last is EPIC. Exercise or excess post-exercise oxygen consumption. Let's say you've just exercised. You ran away from this bear successfully. It hasn't been doing its cardio. It eventually fell off, and now you stop running. You don't just immediately stop breathing hard. Anyone who's ever exercised for a while knows you continue breathing pretty hard for a while afterwards. Why is that? You've accumulated debt. Right? you used a lot of resources early on in that exercise that now need to be replenished. You rated your myoglobin for oxygen. They're going to get more oxygen back. You rated your creatine phosphate. You need to generate more ATP so that you can make more creatine phosphate and get those stores back. You burnt your ATP down to ADP and then down to AMP. You got to get all of that ATP back. That all takes oxygen. And you burnt a lot of sugar into lactic acid. You only got 2 ATP out of that. There's like 36 ATP inside of an oxygen that you can get at if you've got oxygen. Or in a glucose that you can get at if you've got oxygen. You only got 2 of those. You want to get the rest. So all of that lactic acid has to go to your liver, get returned into glucose, and then burnt using oxygen by the normal pathway to get all of that energy back out. All of that takes oxygen. So your metabolism is increased. Even though you're not running anymore, you are still burning energy at a pretty ferocious rate after exercising. You're burning that energy to replenish your creatine phosphate, to replenish your ATP, to reuse your lactic acid and things like that. And during that post-exercise time, your metabolism can be at 6 times its normal rate. And that can last for up to an hour afterwards. This is sort of what people are talking about when they say interval training, right? So if you hit the exercise hard for just 4 or 5 minutes, even less, even a couple of minutes, you burn up all of that energy inside of your muscles. You then go down to a lower level of exercise that's much more aerobic, that's even sort of resting. Your metabolism stays at that heightened rate for a while afterwards as you're replenishing that energy that you stored. And then as soon as it gets replenished, boom, you hit the high exercise again. Burn away all that stuff. You don't actually have to maintain a maximal effort constantly in order to get a pretty maximal burn, because you're accumulating this debt, then you're paying it off, and then you accumulate the debt, and then you pay it off. And a lot of people think that that's the best way to, the most effective way for weight loss exercise, at least. I haven't seen official papers on that, but it makes a lot of sense physiologically. So, in summary, for this, what you need to do is you need to understand intermediate, short-term, and long-term energy, and you need to know what is going to be supplying energy at each point. Immediate is the ATP you got, the myoglobin oxygen that you can use, and your phosphagen system. Your short-term is the lactic acid, glycolysis fermentation. Long-term is aerobic. You need to understand specifically what myoglobin and the phosphagen system are and what role they play in energy production. You need to understand the general sources of muscle fatigue, both for short and long-term exercise. And you need to know what EPOC is and its role in exercise.